Hey everyone, welcome back to Stat 5616, Statistics and Research 2. I hope you guys are having a great morning, afternoon, evening, weekend, depending on when you're watching this. I hope you're just having a great day. This week, we're going to be talking about a generalized random complete block design. It's just going to be an extension of what we've already seen. Before we get into the notes, though, let's talk about the structure of this week like we have done. Homework 3 solutions will be posted Monday morning. This week, you're going to have 3 videos. This video will probably be the longer of the 3, where we're going to be talking about additivity, non-additivity. Then we'll be talking about the generalized random complete block design, mouthful if you haven't noticed, model, and the ANOVA. The second video is going to be talking about testing the interaction. That will make more sense when we get there. And then the third is going to be talking about contrast again, which I think is a great idea because I've noticed a couple of questions on contrast throughout the class thus far. And as normal, homework is going to be due Saturday by midnight. I believe those are all the class announcements. If not, just check Slack or Canvas and you'll be up to date on any new news. So let's get started on today's lesson. All right, Lesson 4A. In this lesson, we'll be introducing the generalized random complete block design, or GRCBD, which is just an extension of the randomized complete block design, or RCBD. Specifically in this lecture, we're going to be talking about additivity versus non-additivity, as well as the model, some notation, and the ANOVA for the generalized complete block design. Okay, but let's talk about some of the designs that we've covered thus far. We've talked about the completely randomized design, which only has one treatment factor and no blocking. That was lesson 2. Then we introduced the idea of a blocking factor with the randomized complete block design. That is, we said there's some factor that will impact the study. And again, our block is not of what's interest to us, but we're just trying to block out extraneous sources of variability to help us understand our treatment. And the key factor with the RCBD is that we only have one replication. We just have a single replication per treatment block combo. Okay, so if we were to look back at our insect design from lesson 3, let's just do a little recap from lesson 3, where our goal was to see the difference, or to see if there was a difference between 3 insecticide treatments. We had these different plots, and we thought that from plot to plot there would be a lot of variability, so it's a very heterogeneous between plots, but within plot it's very homogeneous. So we're assuming that all 3 of these rows, which we're applying the treatment to, look very similar. So we could have treatment A, B, and C. And so this was a random complete block design. How we're going to differ is that the generalized random complete block design still only has one treatment factor, still only has one block, but now we're going to have multiple replications per treatment block combo. So how that would look in our insecticide example would be, right now we just have these 3, so this would be one replication. What we would end up doing is adding an extra 3 rows to this plot and labeling them with treatments. So now within this block, we have 2 replicates of treatment A, 2 replicates of treatment B, and 2 replicates of treatment C. Now, you would also have to make 3 more lines here, 3 more rows here, and 3 more rows here. Of course, so that everything is, we get a balanced design. Now, the multiple treatments becomes important because in the RCBD, so before we added these multiple replicates, if we see a difference in treatment A in plot 1 versus treatment A in plot 4, we assume that there's only a block effect. So if we were looking at this treatment A and let's say this treatment A, we'd assume that the difference is due to the block of maybe this goat and maybe the shade. But now in the generalized random complete block design, GRCBD, we can look at the treatment of A's replicates in plot 1, and they should be relatively the same because we're assuming these are all homogeneous. But if there's a difference, we are able to actually look at the block treatment or treatment block interaction. Okay. So by having more replicates, we are able to investigate more. So let's talk about additivity and non-additivity. So additivity, again, remember in our random complete block design, RCBD, we had an interaction plot, which was plotting the estimated cell means versus the treatment. So treatment's down here, overlaid by the block. So the block are each lines. And in the CRBD, these are always parallel. They're guaranteed. And then that's because of how we set up the design. So if treatment B is better than treatment A in this block, then treatment B is always gonna be better than treatment A, and treatment B is always gonna be treatment A. How I look at it is this slope right here for each line is the same, hence they would be parallel. Same thing here, B is always better than C, B is always better than C, B is always better than C. And these slopes are the same. Now, if we're worried about that this isn't the case, and we would expect that the difference between plots would differ, we need to start worrying about the interaction. So let's go back to this insecticide example right here and see if I can make my point clearer. So with this insecticide example, if we were concerned about the effect of treatment A depending on the plot, or another way is if we were worried about the effect of insecticide A or treatment A doesn't have the same or doesn't behave the same depending on plot, okay? And so with that, insecticide A could be better in this plot compared to B. And then maybe, let's go down to plot 3. So A is better than B in plot 1, but maybe in plot 3, because of all this drainage, treatment B is better than treatment A. And then maybe up here, treatment A and treatment B might be kind of the same because of the shading. Who knows why? And so the whole idea is if we want to see if there's a difference between A and B based on the plot, so the treatment block interaction, we need replication, okay? So if we look at our non-additivity, so here's our non-additive, this is what a non-additivity interaction plot would look like, roughly, kind of the overall idea. And so if our cell means that we plotted are changing from block to block, so again, these are our estimated cell means. And we'll talk about how to estimate those in a little bit. But if we look at treatment A and B, they're kind of similar going from block to block. These slopes are pretty similar. But when you go from treatment B to treatment C, you'll notice in this block, treatment B is better than C. B and C have no difference. And then in this one, this top block, we'll see that treatment C is actually better than B. Okay, so in order for us to tell the effect of treatment, I have to tell you what block we're also in. We don't have to do this with the RCBD because it's an additive case. And because of how we set it up, we are always going to have parallel lines. But here in the non-additive design for the GRCBD, if we compared treatment B to C, B is better in the lower block. Again, C and B are about the same in the middle, and B is worse in the upper block. And so here, what we have is that the pattern of the estimated cell means changes from block to block, which implies we have non-additivity or what we call treatment block interaction. I might also interchange this as block treatment. Again, it's the same thing. So treatment block or block treatment interaction, same thing. I just flip the words sometimes when I talk. Okay, so let's go to an example and understand the design and how we're setting it up. And then we'll start to talk about the model. So here in the reaction time, which will be our main example for this week, we want to study the reaction time under the influence of alcohol, and age is thought to be a factor that could affect the time. That seems reasonable. The test subjects or individuals were classified into 3 age groups, 20 to 39, 40 to 59, and 60 and over. In each age group, each treatment, 0 ounces, 1 ounce, or 2 ounces of alcohol was randomly assigned to 4 individuals, okay? And the following results were obtained, okay? Now, I haven't shown you guys the actual data. That's gonna come on the next page. I really wanna talk about how we got here, okay? And I wanna talk about our treatment factors and all that. So if you wanna pause the video and try and fill these out by yourself, that would be a great way to practice for maybe our midterm and final, so you understand what your treatment factor is and all that. But if you don't want to pause, here we go. So our treatment factor is going to be our alcohol level. Our treatments will be 0 ounce, 1 ounce, and 2 ounces, okay? Our blocking factor is going to be our age, which is going to be represented by the green square, the purple square, and the orange. So our blocking factor is age. And our blocks are 20 to 39, 40 to 59, and 60 plus. Now, again, we're assuming in this study that all these subjects are homogeneous as possible, okay? So again, our blocks are represented by the squares, and our treatment, we'll say blue would be our 0 ounce, red will be our 1 ounce treatment, and black will be our 2 ounce treatment of alcohol, okay? Our EUs, which is our object in which we're applying our treatment, is our 36 individuals. Our observational unit is the object in which we're getting our response from. Our response is reaction time. Our reaction time is coming from our individuals. So our OUs are our 36 individuals. Okay, now let's talk about replication per treatment. So again, our treatment is represented by our different colors. And if we were to count, let's say just the blue faces, we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So here we would have 12 replicates per treatment. And again, we're under a balanced design, so we'd expect that the red would also have 12 and the black faces would also have 12, okay? Now, our replication per block would be 4. Because if we looked inside this block and we counted all the blue faces, 1, 2, 3, 4, we have 4 blue faces or 0 ounce treatments within this block. And so thus we have 4 replicates per block. We also denote this as little n. We'll denote our number of treatments, T equals 3, and our block B, little b equals 3. All right. Again, this is a generalized random complete block design. If we, let's say we only had these 3 people, these 3 people, and these 3 people, so getting rid of the people I'm covering with my fingers, then it would just be a random complete block design because it would only have 1 treatment in each block. Okay, and recall that we can look at the replicates across the blocks. So the similarity between the random complete block design and the generalized random complete block design is that we have a blocking factor. In this case, it will be it would be the age. The difference is that we have the replication, which will allow us to access and understand the block treatment interaction, which we'll talk more about. In this case, the block treatment interaction is, does the influence of alcohol differ depending on age? And so does the treatment of 0 ounce, 1 ounce, 2 ounce in, let's say, this block behave the same as maybe these two blocks? Okay, so again, let me bring back up my additivity. It's not that the shift, so in the additive design, we noticed that you could just have a shift from block to block. That's not what we're interested in. We're interested in, does the slope from A to B change from block to block? So I like to think of additivity as the slope. If the slopes from treatment A to B are the same across the blocks, then it will be additive. But if they're not the same, then that's when non-additivity comes into play. Okay. So again, it's not, is treatment A always better than treatment B regardless of the block? We're looking at how the block is going to impact it. Okay. So our total number of experimental units would be 36 because it's our number of treatments, which is 3, times our block, which is 3, times our number of replicates per block per treatment, which is 4. So we have 36. And here's our data and what it looks like. This column right here is how they randomize it. So here's the block, BLK, and they randomly, and they did their randomization. Okay, and then here's your response. Here's your cell means, and then here would be your treatment means down here. Okay, so one more recap, and we'll keep going over additivity and non-additivity. Is that non-additivity, additivity or treatment block interaction is when you change the alcohol level within an age group. The pattern of the change for mean reaction times differs from one age group to another. So the effect of alcohol changes based on your age group. And our reaction time will be investigating the alcohol level age interaction if it's of interest. And again, recall we can do this in a generalized random complete block design because we have replicates. Specifically, we have 4 per treatment. And then if this was a random complete block design, we would only have 1 replication per treatment within block, and our treatment block interaction we wouldn't be able to do because we would only have 1 replicate. So thus far, we've really talked about additivity and non-additivity, and it will hopefully make more sense as we continue throughout this week's lesson. But now let's talk about the generalized random complete block design in terms of its characteristics, its parameters, its notation, the model, and ANOVA. So we've seen this kind of table before with our other ones. Just a little recap. We have 1 treatment factor, and it can be a combined treatment factor. We have 1 block, and we have block-wise randomization and replication. This is the key part that allows us and distinguishes the difference between a RCBD and a GRCBD, okay? Our parameters are gonna be little t for treatment, so it's number of treatments, little b for the number of blocks, and the blocks have size n times t, where our n is the number of replicates per treatment within each block. So if we went back up to our reaction, it would be the number of little blue faces. And then capital N is their number of total experimental units. If we look at some of our notation, we now are going to add we still have our Yij, but now we have this K, which is going to be the index for the replicate. Here's some summary statistics. Again, I don't expect you to compute these by hand, but I know for some people, especially me, looking at the formula does help me understand what's going on. So it's there for those that would help. Now let's look at our model. So we still have our response, we still have our overall mean, mu, and we still have our random error, which we're assuming is normal, centered at 0, and has some variance. You could also do standard deviation. I just prefer writing it in terms of variance. That's just a personal preference. No big deal there. And then the real thing we want to keep looking at, because what's been changing over the last couple of weeks, is this internal part, or the model effects. And so we still have our treatment effect, which we saw in the complete randomized design. And we have our block effect, which we saw in our randomized complete block design. We added that when we were doing that. And now we have this new term, which is our interaction, which is now being added because we have replicates. So again, with the alcohol example, this would be saying the effect of alcohol changes depending on the age. So the treatment 0, 1, and 2 differs across the blocks. Again, in order to do any analysis in statistics, we have to estimate our parameters because our parameters represent the truth. So we have to do some estimation. The one thing I want to point out here is our estimated cell means. Again, this will be used in our interaction plots, which are going to be super important when we're looking at the GRCBD. Okay, so if we recall, in the RCBD, our mu hat ij looks something like this. So it was the treatment mean plus the block mean minus the overall. And the reason we had to do this was because we only had one replicate. But now in the GRCBD, we have replicates, and so we can do an average of that over the cell mean. Okay, what I mean by that is if we go back and look at our data, here would represent the treatment. This one row would represent the number of replicates for this treatment in this block. And so we can average over these to get our estimated cell mean. This estimated cell mean now comes into play right here in our interaction plot. And so our estimated cell means kind of has more of an intuitive and simpler formula than when we were talking in the randomized complete block design. All right. Here we have, again, how we're going to calculate our estimated cell means, which we plug into our interaction plot. Again, it's just averaging over the replicates given a specific treatment and block. We also have how you would calculate the treatment effects, the block effects, and interaction. I wouldn't expect you to do this by hand, but again, for some people, this might help connect and make connections. It also leads us to our total sums of squares, which is going to measure the variability of all of our sources. Now, again, notice that the total sums of squares is model independent. That is, there's nothing from the model here. All we're doing is taking our observation, minusing it from our overall mean. Okay? And our sums of squares is now broken into the sums of square treatment, sums of squares block, sums of square error, and our new term, sums of square between the block treatment, or this is the interaction right here, okay? Our sums of squared error is still measures the variability due to the unexpected source. Our sums of squares treatment is still telling us about the variability due to the treatment effect. Our block is still telling us the variability due to the block. And now our block treatment interaction is going to measure the variability due to the interaction effect. Okay, and then that leads us down to the classic ANOVA table, where we have our degrees of freedom, our sums of squares, our MSE, and our F-stats. Again, recall that if we were to add the degrees of freedom, we would get the total. If we were to add the sums of squared, we get the total sums of squared. Our mean squared results are our SS, or sums of squared, divided by the respective degrees of freedom. Now let's talk about the F-test. We've done an F-test for the treatments, and that made sense. And then last week when we introduced the block, we talked about how there's no F-test. But the interesting thing here with the generalized complete block design is that even though we're not testing for blocks, we can test the block treatment interaction, okay? And so that's why we're gonna have this. Now, let me see if I can try and convince you of why we are allowed this test, but not this test, okay? I'm gonna try and do this again through stuff that we've already seen, which is the expected mean squared. So when we're testing for the treatment, which would be looking at the MST over the MSE, our null hypothesis is that our alpha i's equal 0 versus our alternative, which is alpha I doesn't equal 0 for some I, right? And so under the null, this cancels out and we're left roughly with the sums of squared error, which we then divide by our MSE. And so it'd be sigma squared over sigma squared under the null. And so that's valid. In our block, which we talked about last week, there is no sigma squared epsilon. And this is based on how we did our randomization. And so what happens is this becomes invalid. We have, if this goes to 0, it's 0 over that, and that just doesn't make sense. Now, when we look at our block treatment, our null is our alpha or beta, alpha beta ij is going to be equal to 0 versus our alternative alpha beta ij not equal to 0 for some ij. Now, under the null, this would go to 0 because that's pretty much saying this is 0. And we would be left with this sigma squared over epsilon. And so this is going to be valid because it would be sigma squared over this sigma squared. And so really it's because based on how we randomize, the block doesn't have this error term. And so that's why we're allowed to have a test of block treatment, but no block. Now, that's going to end this lesson. In our next lesson, we're going to talk more about this test of interaction. And then the lesson after that, we'll be talking about contrasts. I hope you have an amazing day, and I'll see you in the next lesson.